Welcome to Reductio Ad Absurdum. This is the next procedure in terms of a proof that we're going to be taking a look at here. And you've already seen the beginning of this, but we'll go ahead and go over it again, just because, again, there's been a spring break and a potential apocalypse between here and then. So here we go. The example, again, I'm going to use is of Reductio is this nice Sudoku puzzle. And again, a brief refresher of the rules. All of the big boxes that you can see here, and as well as every row and every column, have to have one and only one of the numerals 1 through 9. And, again, that's the way it goes. So if you look at those two cells, you notice that one of them has to be a 2 and the other has to be a 4, because that's what's missing both out of its well, it's not a quadrant because there's 6 of them. Sextant? I don't know. There's got to be a word for that, and I should know, but I don't. And also because in its column, it's missing a 2 and a 4. So we know that one of them has to be a 2, the other has to be a 4. Okay. Now, of course, this is based on the rules of Sudoku, which if you simply disregard those, it's a much easier puzzle. No rule is broken either way, at least not immediately, that we can see by having one of them be a 2 and the other one be a 4. And so it's not really clear or obvious which one is which at this point. And so we're going to do the first step of a proof by contradiction. We make an assumption, right? Just like in conditional proof, we start by making an assumption. Reductio is going to start the same way, make an assumption. We're going to assume that the upper cell is a 2, which would of course make the lower one a 4 by the rule. So we're going to say assume, for the sake of argument, just to see what happens, we're going to assume that the upper cell is a 2. And so now we test the implications of our assumption. We see what else has to be true as a consequence of assuming that square was a 2. Well, first, this green highlighted cell here, that has to be a 2 because a 2 has to occur in each 3x3 box, and that's the only space on which it is allowed due to our assumed 2 in the box to the left. Okay, again, we want to have only one of each numeral in each row or column, and because we have a 2 here, right? That means there can't be a 2 in any of these other boxes, which means that this is the only one left, and that absolutely has to have a 2 in it. Okay. And so now notice these blue cells up here, okay? Now we're going to test the implications of our assumption. We're going to see what else has to be true as a consequence of our assumption. Okay, now again, notice those. By rule, okay, there has to be a 2 in one of them. But of course, this 2 here, which was forced by our assumption, would take those 2 boxes out of consideration for having a 2 in them. And of course, this one here that is part of our givens, this is what the puzzle makers gave us because it's in black instead of blue, that, okay, takes out this entire area. None of that can have 2's either. So that means that this whole area here, cannot have a 2 in it, and it needs a 2 in it in order to follow the rules. And so we've done something in making our assumption, we've created an impossible situation. And so that 2 in the lower green cell, of course, is only present because it was forced by the assumption we made before. And so because the assumption that we made forced us to break the rules, we have to conclude that it was the wrong assumption, right? Again, granted, given that everything else is placed correctly. And so if an assumption leads you into some kind of absurdity, then we can conclude it was the wrong assumption. If it was wrong, that the upper cell was a 2 and that the lower is a 4, then that means that it has to be right that the upper cell is not a 2, that is, that it's a 4, and that the lower one is a 2. And once that assumption is corrected, that is proved by contradiction, just as we have, the other cell follows from the rules and the process of disjunctive syllogism. So process of elimination actually takes us all the rest of the way there. So really, again, Sudoku involves only 2 logical operations, right? We have disjunctive syllogism, which is, P wedge Q, not P, entails Q. And then this notion of reductio ad absurdum, or proof by contradiction, that we just walked through. Although I guess the word Sudoku, it might be actually Japanese for this, I don't know, I doubt it is. But it's a shorter and more elegant name than disjunctive syllogism punctuated by reductio ad absurdum, okay? Marketing. Okay, so here's how it looks in one of our proofs with our format. And again, the idea behind Reductio is to prove that something is false because it would be absurd if it were true. That's the whole idea behind proof by contradiction. It's a very simple idea. And in logic, there's only one kind of absurdity. It's a contradiction. And so if something is absurd, that means it must be a contradiction. That's the only kind of absurdity we really care about here in logic. And so what that means is that, a contradiction in our case is any conjunction where one conjunct is the negation of the other. That's what we're going to count as a contradiction on our proofs. You're going to have something where you have a thing and its negation. And that doesn't have to be just an atomic sentence like P and not P or not Q and Q, right? It can also be some complex, such as P wedge Q and not P wedge Q, right? Again, that's a conjunction of a thing and its negation. So no matter how complicated it is, if it's a conjunction of a thing and its negation, then it's a contradiction, and we can use it for the purposes of reductio ad absurdum. And so here's the mental process. What you want to do is when you want to introduce a negation, okay, remember RAA is a negation introduction rule, then that's when you'll use it. And your first step, make an assumption. Okay, and of course you should put in the notes that it's for reductio because you can only discharge an assumption made for reductio by getting a contradiction. Just like with conditional proof, when you assume the antecedent, and you can only discharge that assumption once you have derived the consequent of the conditional that you were trying to prove. So conditional proof discharges by getting the consequent of the conditional when you assumed the antecedent. Reductio introduces a negation into of something because you've assumed it, you've derived a contradiction, right, which is the second step here. So you after you make an assumption, you derive a contradiction, and that contradiction allows you to discharge the assumption. Right? And so then you'll discharge the assumption and you will conclude the negation of the assumption. Okay? So you'll assume the opposite of the thing that you want to end up proving, the thing you want to end up adding into the proof. And then you will prove that assuming that thing that you just assumed results in some kind of a contradiction. It will, if you really can prove the thing you're trying to prove. And then you discharge that assumption once you bring about a contradiction. You say, hey, look, if you assume this thing, you get a contradiction. So therefore we mean not that thing. You just slap a negation on it and then discharge your assumption. There it is. And so again, remember, RAA is a negation introduction rule, just like conditional proof is a conditional introduction rule. You'll use it to introduce a negation into something. You'll use it to bring something into a proof that just isn't already there. And so here's a sort of abstract view of how that always works in a proof. Okay, so on some line, we'll call it, say line 1, for example, here. Notice line 1 depends only on itself because we've just, said the justification for our purposes is an assumption. That's always the first step of a reductio. And so, again, you're going to just assume something, right? And we're just, put this capital P here to indicate, the one here, to indicate any claim in S, any sentence of S, right? And then of course you want to note that this is for reductio because you're going to say, okay, I can discharge this assumption when I get a contradiction because that's for reductio. Okay, and then of course you've got these little dots here, the ellipses, have yeah, ellipses, they indicate, again, some time later in the proof. And then at some point, you have some later line where then if you get some kind of a contradiction, something that is a negation, a thing and its negation as a conjunction, a lot of times conjunction introduction is going to be how that happens. You'll have, something and you'll have its negation on another line. You'll join them together. You'll note over in the notes that this is a contradiction. And then your dependency numerals will, you'll sort of discharge that assumption. So on some later line, then you can say, well, because we assumed P, we got a contradiction, we're going to conclude not P using line 1, the line on which you made the assumption, the line on which you derived the contradiction, and the rule reductio ad absurdum. Okay, that's how it looks on a proof. Let's take a look at an example. And so a note about RAA is that it's really the most useful and versatile rule that we have. generally, if you can't figure out how to proceed in a proof that looks kind of complicated, it looks like it might not just be a simple matter of manipulating like modus ponens and modus tollens or whatever, you can usually learn something by simply assuming the negation of the thing that you're trying to prove and then just looking for a contradiction. Even if there are perhaps other straightforward ways of doing some of these kinds of proofs, they can still work using reductio. It's there's often more than one acceptable way to do a proof, and a reductio, if it works, will work, right? That's it's very often useful, and even if it doesn't necessarily help you do the proof, it helps you learn something about how some of these things relate, and oftentimes it'll get you onto the right track. And so what we're going to do here is we're going to show that the sentence if P then Q, the sentence if P then not Q, that we're going to show that that entails the sentence not P. Okay. And so we're going to start off by setting up our proof, setting up our line numbers here. That's always the easy part. Dependencies, right? Because they're both givens, right? Our line 1 depends only on itself, and line 2 depends only on itself. Okay, and so everything's all set up. So our next step, of course, is an assumption. Okay, and we're gonna note that we assumed it for RAA. That's the purpose. So we know we're looking for a contradiction now. And so you should be looking at the proof and thinking to yourself, gee whiz, how could I get a contradiction? Because remember, the reason we're assuming P here is because, right, the thing we're trying to prove is not P. We're trying to introduce a negation. And that's where, again, sometimes the way that we have these rules, just basically one negation, one introduction for each of our connectives, it helps to take a lot of the thinking out of it. And so if you need to introduce a negation, then you gotta use the negation introduction rule. That's RAA. So we're going to assume P so that we can then introduce a negation to it. So if we can assume P, say that assuming P gets us a contradiction, then we'll say, well, then, not P, right? Obviously, right? So if P is contradictory, then not P would have to be true. So take a look again. If you have to pause, right? Pause the video for a minute and really think, what's the next step here, right? How can I get a contradiction? Okay. So I hope this is what you were thinking, because you thought, okay, now we actually have something to work with on these top 3 lines. We have line 1 and line 3 that has a conditional and the antecedent of that conditional. We also have the same thing on line 2. We have a conditional and the antecedent of that conditional. And if you just use modus ponens on both lines, you're going to get Q, okay, which is what we have on line 4, and not Q, which is what we have on line 5. Again, using modus ponens both times. And so now you'll notice that on line 4 you have Q, line 5 you have not Q. Now all that's left is to put them together to have a contradiction on the same line. And so we're going to use conjunction introduction to stick them together. And so remember, when you're filling out your dependency numerals, that line 4, right, because it cited line 1 and line 3, it depends on what line 1 and line 3 depended on, which is 1 and 3. Okay. Our dependencies for line 5 were, since line 5 depended on 2 and 3, it depended on what line 2 depended on, which is 2, and what line 3 depended on, which is 3. And then here on 6, because line 6 depends on lines 4 and 5, it depends on what lines 4 and 5 depended on, which is 1 and 2 and 3. But of course, this is a contradiction. Q and not Q absolutely is a contradiction. So that means that the thing that led us there couldn't possibly be true. And the thing that led us there was this assumption that we made on line 3. And so we're going to discharge our assumption, number 3, and we're going to conclude the opposite. We're going to say if P led us to a contradiction, well, then not P. And that's, in fact, what we have on line 7. So that's line 3, right, which is the line where we made the assumption. Line 6, which is where we got the contradiction, and the rule reductio ad absurdum. And because this depends on line 3 and 6, it depends on what line 3 depended on, okay, which is just 3. And of course, what line 6 depended on, which is 1 and 2 and 3. And of course 3 gets discharged, right? So we get to just sort of X that out. We don't have to use that. And so we have to just copy it over 1 and 2 as the things that line 7 depends on. And there you go. Since 1 and 2 are our givens, it's okay that we end the proof with a line that depends only on those things. And so what we've effectively proven is that if P then Q and if P then not Q entails not P. Good. So that is an example of how reductio ad absurdum works in all practicality.